Hey class, here's a help video for you guys all based on problem 25 from the homework. Quite a few people have been asking me about this, so I thought I'd just go ahead and take some time to break it down and give you guys some pointers on it. So in this problem, we're asked to figure out or determine three different things. We're asked to determine what the tension is in this cable, so I'll call that force T. We're also asked to determine the reaction forces in the y direction, Py, here at the pivot, and Px. Okay. Additionally, we can see that there's a weight force from this crate, which I'll call WC for the crate force, and then there's also a weight force from the beam, which we can assume is going to act at the center of the beam, which we can call WB. Alright, so we're trying to determine T, Px, and Py. So we're going to have to be looking at using the sum of the forces, the sum of the torques, and some of the forces X and Y and some of the torques. So I'm going to go ahead and draw another free body diagram since this one's a little bit kind of crowded. I'm going to draw it a bit larger here. So here's my beam. Okay, we know that it makes a 30-degree angle, so here's my X and Y axes. And we know that this is a 30-degree angle. So my tension force, let's switch to blue for tension force. So my tension force is acting up in this direction. Okay, and we can observe that the angle between the tension and the beam, so if we make sort of a dashed line here, we're told that this angle here is 50 degrees, and this angle down here, by geometry, is going to be the same as our angle here, so it's actually also 30 degrees. So the total angle there is actually an 80-degree angle. Okay? So that's our tension force. Our point P down here I'm going to use as my axis of rotation for doing the sum of the torques. That is where I have my Py and my Px, but the torque from Px and Py are 0, so when I do some of the torques I won't have to worry about it. We also have the weight of the beam at the center, and then also we have the weight of the crate at the end. And so I'm going to go ahead and call the length of my rod L once again. Even though we're not given that value, we can just give it the variable L to represent the length. Alright, so if we want to set up the sum of the torque, we know or can figure out that the sum of our torques is going to be equal to the torque from the tension plus the torque from the crate plus the torque. Apparently my laughing track in the background is not quite calibrated correctly, but I'll have to make a bad joke and see if they laugh at the right time. So, yeah, anyway, sum of the torques is going to be the tension, the crate, and the beam, and they're all equal to 0. Alright, so let's go ahead and try to figure out each of these. So we know for any given torque, it's going to be the force multiplied by the perpendicular distance. Alright, so if we look back at our diagram here, we can see that the tension force here is going to cause counterclockwise rotation. So that's going to be a positive torque. If we define the perpendicular distance to the line of action of our tension force as being L sub t, so I'll call L sub t is the perpendicular distance to the tension force. What we can say then is that the torque T here, which is positive, is going to be the tension force multiplied by the perpendicular distance, LT. And that distance is going to be some distance kind of like this, which I'll show you in more detail here in a minute. It's hard to see on this drawing because it's getting too crowded once again. So that's LT. We're also going to have a perpendicular distance to the crate here, and so we'll call that LC, the perpendicular distance to the weight of the crate. And then lastly, we have the perpendicular distance to the weight of the beam, which is here, and we'll call that L sub B, which is the perpendicular distance to the weight of the beam. Okay, so if we can figure out what each of these different perpendicular distances are, we can plug those into our equations to try to solve. So, continuing on, now that we have LC and LB, we can observe from our drawing that LB and LC are both going to cause clockwise rotation, so they're both going to be negative torques. So we're going to have a negative torque from the crate, which will be just equal to the weight of the crate multiplied by LC, and then we're going to have a negative torque due to the weight of the beam multiplied by its perpendicular distance LB, and those will all, the sum of all of our torques is still going to be equal to 0. Alright, so we got a good start and we can see what's going on. Now let's try to figure out what each of our L distances are. So I'm going to draw yet another picture to help us with that. Actually, that's not where I want it. So I'm going to draw it over here so I have a little more space. So if this is our beam of length L, our perpendicular distance to the tension force. So our tension force is here, remember, and we decided this has a total angle of 80 degrees. And so if we identify the line of action of that force, I'll do it maybe in yellow. The line of action of the force is here. And so we want the perpendicular distance to the line of action of that force. So the perpendicular distance is going to be some distance here that's perpendicular to that line of action. And so what you end up with is a right triangle. And so we have a right triangle here that has a hypotenuse length L and a right angle at this point, and then we're given this angle as being 80 degrees. And so what we can find then is that our distance that we're trying to determine, LT, which is the length of this side, is just going to be equal to the hypotenuse L multiplied by, since we know this is an 80 degree angle and that's the opposite side, L multiplied by the sine of 80. Similarly, we can make triangles for the other two forces as well. So you have over here the weight of the beam, or excuse me, the weight of the crate, its line of action. Let's choose yet a new color for its line of action. Its line of action is here, and so the perpendicular distance that we want is this distance here. And again, we know this is a 30-degree angle, and so we can see that the perpendicular distance, this one here that's LC, is just going to be equal to L multiplied by the cosine of that 30-degree angle. And then lastly, here we have the weight of the beam, which you can see this is the line of action, and so the distance that we want here is LB, and you can see once again that LB is just going to be equal to L multiplied by the cosine of 30. So now you have an equation up here where you can plug in each of these different values. You can plug in LT, you can plug in LC, and you can plug in LB. Knowing the weights given to you in the problem, you can actually solve for the tension force just by doing some of the torques. And then to solve for the last two items you're asked for, it just becomes a simple sum of the forces. You have sum of the forces in the x direction equals 0, and sum of the forces in the y direction equals 0. Alright? And what you have, if we looked back up at our first free body diagram, in the x direction, all you're going to have is px and a component of t. So you'll just have px minus tx equals 0, and then the y direction you're just going to have py, which is going up. If we notice, the y component of t is going to be in the vertical direction, so you'll have plus ty minus the weight of the crate minus the weight of the beam equals 0. So go ahead and try to solve these to figure out what your tension is and what your x and y forces at point P all are. Hope you guys have a box-worthy day, and let me know if you have additional questions.